and theta 1 over theta 2 is equals to n2 over n1. Therefore, T2 is equal to J d squared theta over dt squared theta over dt plus k theta. All these are theta of t. Let me call this, okay, it's okay, j, d, and theta. Or T2 of s is equal to s squared j theta 2 plus s d theta 2 plus k theta 2. This is theta 2 of t, this is theta 2 of s. So this line is of s, this is of t. Now, I want to refer this to T1. So I'll say T1 is equal to T2 N1 over N2. So T1 is equal to S squared J theta 2 plus S D theta 2 plus K theta 2 times N1 over N2. The question was telling us transfer function theta over t, theta 1 over t1. Meaning, now I want to express this theta 2 into theta 1. So theta 2 is equal to theta 1 n1 over 2. So I express theta 2 with theta 1. So t1 becomes s squared j theta 1 n1 over n2 plus sd theta 1 n1 over n2 plus k theta 1 n1 over n2, all this multiplied by this n1 over n2. So T1 is equal to S squared J theta 1 n1 over n2 squared plus S D theta 1 n1 over n2 squared plus k theta 1 n1 over n2, or theta 1 over t, this output, this input, is equal to 1 over s squared j n1 over n2 squared plus d sd n1 over n2 plus d squared k n1 over n2 squared, which is the transfer function. Actually, I think I was repeating myself by referring this j, I multiply by this again twice, and then we are having n1 over n2 squared 2 times. So this is how we go about that question. So Today we are going to go through a new topic. It's time domain analysis systems. We have been dealing with obtaining the transfer function. And we say that if you know the transfer function and you have an input R of S, then the output C of S is equal to the transfer function G of S times H of S times R of S, sorry. Input R of S. The transfer function is G of S. And this is what for the last three topics or in time domain analysis, we want to see the behavior of the signal in time domain. How does it behave in time domain? So you have your signal R of t. To get R of S, the Laplace transform of R of t. To get R of S. And then you pass your R of S through the transfer function G of S, you get C of S. So to see the time domain, C of t is equal to Laplace inverse of C of S. And you see the behavior, how does it behave? How does C of t behave? So we have two responses. When you're dealing with circuit analysis or circuit methods theory, you did the transient response. Transient response is what happens immediately this change in state. That is, for example, if you had a capacitor like that, supplied to some voltage, volts, and these are capacitors. What happens if you switch on? Is that charging? It starts charging, So within some time, the voltage of the capacitor, for example, VC, is increasing and it is changing. But after some time, it almost becomes constant. So this is a transient state. What happens in the initial state to final state? And then steady state is what happens as time tends to infinity. So in the capacitor, for example, you see that the voltage is increasing rapidly, is changing rapidly. But as time tends to infinity, it has reached almost a steady value. So there are two responses, the transient state and the steady state. The transient state is that which goes from the initial state to the final state. And I have used the capacitor to illustrate that when you are charging a capacitor, the voltage across the capacitor changes very rapidly within a very short time. After some short time given by what we shall see shortly, known as time constant, it stabilizes. It reaches, the behavior now reaches almost a constant value as time increases. So steady state and the transient response. Steady state response. So the total response of the system is given as total response is steady state, transient, plus steady state. Transient plus steady state. We are going to look at 3 examples. When you have impulse response, and step response for first order, and the system and the response second order system. Now, the first thing that we do is to do modeling to obtain the transfer function. We do modeling to obtain the transfer function, and this is what you have covered. The second, we apply some test inputs. Apply an input can be impulse input, impulse input, impulse. We can have a step is just this here. A change. Step can be a change, can be a force, it can be a voltage. It increases just from 0 to a certain value A. We can have a sinusoidal input which changes, etc. So I've said that we'll just limit ourselves to impulse and step response. Subject your system to some input, and then you study the output. So you supply R of t to a system G of t, and then you see what is C of t, or R of S, G of S, and then your output C of S. So that's basically what you do. You model the system to obtain G of S, choose a suitable input which is R of t, and then observe the output C of t. How do you choose your R of t? The signal. The system will be subjected to some inputs, some inputs. The system which you are studying may be subject to some inputs. The inputs which the system is in its, when it will be operating, during its operation, it will be subjected to some kind of input. That becomes a very suitable kind of test signal. If your input will subject, if your system which behave sinusoidally like this, then a sinusoidal input becomes the best choice for test signal. If you are going to have impulses, short impulses, then your system, the best choice for test signal will be impulse. But for us, for our study, we'll just study 2 inputs, the impulse input and the step input. Now, control systems involve storage elements. You saw that for capacitor, Vc is equal to C dV over dt. And we also saw that for damping, the force is equal to B for a damper, dx over dt. So these are energy storage elements. They don't respond. A spring responds immediately. Like if you supply an input, the output just responds immediately. But for a capacitor or for a damper, if you supply a force, this is a step force, step input. For a damper, you supply some force. This is input force. You expect some displacement. The displacement will not follow immediately. It will delay because of the energy storage. But if it is a spring, if you apply a force to a spring, the output will almost be sudden. This is force, this extension or X displacement. Because the spring, the output F. No. What am I talking about? This is the input force. Is equal to. Oh no, I'm talking about something different. So the input should be force. The output will be. Yeah, I think should be the extension, because this is X. You apply some input force. The output, which is extension, should be proportional multiplied by a constant, which is the extension, which is X, the distance. But this distance will not be immediate. It will take time. This is sudden. This is because of energy storage elements. The output does not follow the input immediately. There is some delay. There is some transient response. There is some time in which it takes between initial to the final. This is the transient response before it reaches a steady state. If the output of the system at steady state does not exactly agree with the input, then the system is said to have a steady state error. Yeah. If you push a force, if it does not approach as time tends to infinity, it stabilizes at some, and this is the input, this input, and this is the output, which is force times extension. This d times extension, dx over dt. So then we say that there is some steady state error, ESS, steady state error. If it doesn't follow, but in many cases, or in some cases, for some types of systems, you see that as time tends to infinity, the response tracks the input with zero error. You say response tracks input with zero steady state error. But there are systems which have errors. There are some systems which have errors, which is not zero, depending on the input is applied. So they say the error is not zero. It doesn't agree, and we say that the system has some error, and we may not mention that in this, but you can check the textbook by Ogata. We have position error constants. We have error constants. For systems which has errors, but we will not discuss that. Now, we have inputs. I've said a step input. You call it a step, Step input. It changes like a step in a stairs, If it's force, initially you had applied no force, and then you apply next force, like that. You call it a step step input. We have a ramp input, ramp. We have an accelerating input, like y is equal to t squared. I can call it at squared, at squared, at squared. This is at, where a is the slope, and this is when you say step inputs, unit step, we mean a is equal to 1. We have some impulse. An impulse is defined as a very narrow signal of diameter, not the diameter, but duration, sorry. Diameter is not the right choice of this. Duration. Amplitude. Infinity. It's an impulse. And it's usually defined as of t 0 for t. This time, t is equal to 0 here. And integral from negative infinity to infinity, the t dt is equal to 1. Definition. It means the area of this impulse is equal to 1. Because we cannot have such a signal, we cannot have that such a signal, it is usually approximated by a pulse. By a pulse of area is equal to unity. So if the amplitude is A, then the width is 1 over A. So the narrower pulse, the narrower the pulse, the closer is pulse, yeah. So the impulse response. Actually, in real estate, it is expressed this way, but this is equal. A spike of very short duration, say that the duration times the amplitude is equal to unity. So we have several signals. So we are going to look at the impulse response for first order systems. A first system generally is expressed this way. Say that this is GOS open loop function, so that when you close over, which is equal to 1 over t plus ts times 1, h is 1 here, 1 over t. So that if you multiply through by ts, you get 1 over ts 1. You can express it this way: 1 over t over s. One over t. So this Generally, it can be written 1 over s plus a. Time is a constant. So there is this is just a multiplication factor constant. Factor. And if s d over dt, then these are just a first order differential equation. So this is a first order system where the ratio of the outputs over inputs is equal to 1 over st plus 1. This is a transfer function over first order. Now, we want to study the response to an impulse, input impulse, delta of t. What happens in that case? Let me just get Laplace transform. Just Laplace transform tables. Yeah. You are always given Laplace transform table. So, you want to get Laplace transform of delta of t is a 1. Laplace transform of delta of t is equal to unity. So, to get the Laplace transforms, you'll be given Laplace transform tables. So, you have system, transfer function is 1 over st plus 1. And R of t is equal to delta of t. So what is R of s? R of s is unity from this table. This unity. Delta of t. So it is unity. So C of s is equal to R of s, G of s, which is equal to 1 dot 1 over st plus 1, which is equal to 1 over st plus 1. C of s. Now we need to get C of t is equal to Laplace inverse of 1 over st plus 1. So we come to our table, Laplace table. 1 over st plus 1. Do you have it? You don't have. We have in this form 1 over s plus a. S plus a. So we manipulate this st plus 1 to become 1 over s. You divide by 1 over t. St plus 1 divide over t over t. It becomes 1 over t over 1 over s plus 1 over t, which is equal to 1 over as a multiplier dot 1 over s plus 1 over t. This is a Laplace. Now you can get this from Laplace transforms inverse. Laplace of 1 over s plus a is equal to e negative at. Here, 1 over s plus a is e negative at. This one. So this becomes 1 over t e negative t over t. Our a here is 1 over t. Our a is 1 over t, so it's t 1 over t. And c is equal to 1 over t e negative t over t. Which, if it is plotted down, it is decaying exponential. Decaying exponential. And this is the response. This is the response. Toka. Popo. Niko. So, this is the response curve or first order system to impulse input. This is how it behaves. It shows that if you supply an input, then the output decays with time. Now, supposing you give it a second order, or we give it a step input, sorry, a step input. A sudden, if it's a force, if it's a voltage, if it is whatever, electrical, pneumatic, thermal. So these are step inputs. So our first order system is 1 or Ts plus 1. This is G of S. U of S, we get U of S from the Laplace tables, which is basically 1 over S. This unity, this is a U of T. So it's 1 over S. It's 1 over S. Now, U of T is actually equal to 1. It has just stepped 0 to 1. So we say from t greater than 0, because it does not, it is not, it has to happen at some point. So it is defined as this is equal to 1 from the time you apply the force, and before you apply the force of unity, it was equal to 0. So its Laplace transform is 1 over S. So U of S is 1 over S, and C of S is equal to R of S, U of S, R of S, G of S is equal to 1 over S, 1 over ST plus 1. Now we need to get C of T is equal to Laplace inverse of 1 over S, 1 over ST plus 1. Looking at Laplace table, we don't have that kind of function. But we have 1 over S and we have 1 over S plus A. What we can do now, we can do what is known as partial fraction expansion. Partial fraction expansion. First, you express it in the form of 1 over S and 1 over S plus A. So we have seen that you can express 1 over st plus 1 in this form. So you need to do partial fraction expansion of this by saying 1 over st plus 1 is equal to a over s plus b over st plus 1. This is known as partial fraction expansion. I can now cross multiply through by st plus 1. If I multiply by s and st plus 1, it will cancel. This becomes 1 is equal to, if I st plus 1. So the s will cancel, it will remain a st plus 1 by st plus 1 times s. So st plus 1 cancels to remain b. So ast plus a plus bs is equal to 1. Group like terms. A is equal to 1. A is equal to 1. And bs is equal to negative ast. I've just grouped this ast plus bs to the coefficient of s. So bs is equal to negative st, or b negative t. Hope I've done it correctly. So hope I've done it correctly. Yes. So our solution now becomes a over s, which is 1 over s plus b over st plus 1. B is negative t minus t over st plus 1. I can now express this in the form 1 over s plus a by divided through by t. It becomes 1 over s minus, divided by t becomes 1 over s plus 1 over t. Divide through by t. That is t over st over t plus 1 over t. So this cancels and this cancels. It becomes s plus 1 over t, which is this. And from the Laplace transform tables, you find 1 over s was equal to 1. 1 over s plus a is equal to negative at. Negative a, which is 1 over t. So if you plot this, it is an increasing exponential like this. So you applied a fixed force of unity magnitude. But now the resultant force, which is the output force, increases slowly by 1 minus e negative t. So this is a transient. And as time goes at around this point, it is now approaching steady state. So the output follows the input with some time delay. This is known as the response curve. Now you have applied a step input and you have seen the outputs. The output follows the input, like that. And as time tends to infinity, the error approaches zero, the steady state error. Now, we need to interpret this table. 1 minus e negative t over t. At t, this response reaches 1 minus e negative t over t, which is 1 minus e negative 1, capital T over t, which is 0.632. So at t is 1, at the small t is equal to t, capital T, it has reached 63%. At t is equal to 2t, it has reached 86%. At 3 is equal to 3, it has reached around 94%. Capital T is known as time constant. Time constant. And this t can be found by differentiating this function, and it gives the slope at t is equal to 0. So it can be defined as a time constant. It is defined in relation to the slope of this function. Now, the output rises from 0 to unity. Time tends to unity. That's what you have seen, this right from 0 to unity. The initial slope is 1 over t. The initial is equal to t is referred to as time constant. And it indicates how fast the system tends to reach the final value. There are those systems which take eternity. There are those systems which respond very fast. And there are those depending on the value of the time constant. We have seen that for different times constants, it reaches some percentage of the final value. We can say that at around, in practice, they say at 4 time constants, the system must stabilize. As stabilized, that it has reached steady state. Because it has reached 98% of the final value. At 40, it has reached 98% of the final value. 98%. So we assume that 98% it has stabilized. So usually 4 time constants is taken as 4 time constant is taken as the time the system takes to stabilize or to reach its final value. And how fast will depend on the time constant. And the error is equal to actual minus input minus actual, input minus output. Actual output, input minus output. The input was 1 and the output was 1 minus e negative t over t, which is equal to e negative t over t. Initially, the error is very big. Initially, the error was between this point and this point. But as time increases, the error becomes small and small. This is the error between the input and the output. It becomes small and small. So, As time tends to infinity, you see that this error tends to 0. So steady error will be the limit as time tends to infinity e of t, which is equal to 0. If you recall your Laplace classes, theorems, you can as well, instead of getting, if you are just want to find out the steady state error, you can just get it straight from the Laplace transform E of S without getting E of t. But this is just some additional. This suffices. But if you find that it is easier to approach it from the Laplace transform, it's still okay. We said that this first order system tracks the unit step system, the unit step input with 0 steady error. So as time tends to infinity, for first order system has 0 error to step input. Now, I think a smaller time constant corresponds to a system T small, T large. To a smaller time constant, how fast the system responds. So for a step input, a first order system, the output follows the input on the constant. But as time tends to infinity, the error between the input and the output tends to 0. I said we look at 3 cases. First order system, we have looked at delta of t and u of t. So the last we're going to see second order systems, but with step input. You recall when you were modeling our mechanical system, it was this, it's a mass. And get some extension x. We came up with the second order transfer function, u of x. We came with a second order transfer function. How does it respond to input? It is in form. That is transfer function omega n squared over s squared plus 2 delta s omega n. If you some have the omega n, if you reduce some omega n squared. Of this is a standard form, and they are standard curves. And this is the form that you get even from this, look at the denominator, s squared plus 2 delta. Okay, this has used a different symbol in delta, s squared plus 2 delta omega n plus omega n squared. So second order systems have the denominator takes standard form, even from the Laplace transform tables. Second order systems. Once you express in this form, for example, you can do this 1 over m over s squared plus s fv over m plus k over m. So k over m is equal to omega n squared. And fv over m is equal to 2 delta omega n. Now that you know that omega n is that, you find out omega n, you can get delta. And if this omega n, then you can reduce k, and then 1 k is a multiplication factor like that. So this becomes omega n squared, and then fv over m is 2 delta omega n. So you can get delta. Wn is referred to as undamped natural frequency. Delta is a damping ratio. 2 delta omega n is referred to as attenuation. These are standard terms depending on the response. For the response curve, the behavior of a second order system is described in terms of the damping ratio and natural frequency. The behavior is defined in terms of these two parameters. That's why it is in terms of for plus 2 delta omega n s plus omega n squared. Damping natural frequency. Damping ratio. Now, the denominator polynomial is called characteristic equation, and we are interested. You remember when you are solving quadratic equations, ax squared plus bx plus c was equal to 0. We had read repeated, real distinct, and complex roots. Complex will occur as complex conjugates. So similarly, in this case, we have similar, the value of delta omega n can take different values. Omega n can be between 0 and 1. The value of omega n can be between 0 and 1. And also it can also be greater than 1. But usually control systems are designed such that delta lies between 0 and 1. So depending on this equation, you can have 3 responses. You can have transient response, which does not die out. The output is oscillatory. Delta is equal to 0. Does not die out. Die out. You can have delta is equal to 1. Then the response, you have applied a step input. You have applied a step input. This is the input. Input. And this output. This you applied a step input, the output. Input. Output. But if delta is in between, delta 1, you have applied some input like that. Input. This thing will oscillate. Oscillates at some frequency. And the response will be dying out. So the response will be dying out in that manner. Let me redraw it again. So like that. So that response. So the response will go like this. Comes. So this is damped. Response. So now there's the element of damping. The response is dying out. It's to the oscillation is dying out. The oscillations oscillate at some frequency and it is dying out. It is dying out. The oscillations are dying out. So we have these cases of critically damped, overdamped when delta is greater than 1. When you have real roots now. What real roots? How can I put it? Delta is greater than 1. But control systems are usually designed such that delta is equal to 0 and 1. Is overdamped. When delta is equal to 1, critically damped. Delta 0 and damped. And this is a damped sinusoid. Damped sinusoid. This is the response which most control systems behave this way. Control systems behave this way. Or systems generally, systems. For example, if you can access MATLAB, you can try to see for this system, you can see the response of this. You can give M a value. M is equal to 2, F is equal to 2, and K is equal to 7. And then using MATLAB, you can get tutorials on the internet. You do step function of this system, and then it will give you an output. So you can vary M and F and K and see the different responses. Yeah. Now, so the most common response is the oscillatory, which we are going to discuss this. So This is a short. So this response is associated with some definitions. One is the delay time. A delay time. You see, as the response goes between initial to final, you see, this is the final. This is the final. So at a point here, it reaches 50%. The time it takes to reach 50% is referred to as delay time. Number two, we have rise time. Rise time is a time taken. You see, if your system goes from 0 to maximum, the time taken between 0 and 100, 0 and 100, 0 to 100%. So this time is here. Rise time, TR. 0 to 100% is rise time. But because of this definition is universal, we have those systems which are critically damped, which will not reach 100%. You know, a signal which will never reach 100%. Then instead you can define the time it takes to reach between 5% and between 5 to 95%. Because this kind of system, critically damped, damped, will not reach 100%. The signal will not overshoot. The signal will not go beyond more than 100%. So we define between 5 and 95% or 10 and 90%. So we have three scenarios. For a signal with the damped sinusoids, it is between 0 and 100%. For critically damped, it is between 5 to 95 or 10 to 90%. So this is referred to as rise time. The time it will require to reach from 10 to 90%, 5 to 95, or 0 and 100%. For underdamped cases, we use 0 to 100%, where we have overshoots. For overdamped cases or critically damped, we use 10 to 90%. The rise time. Peak time. There is a point in which the signal reaches the maximum peak, which is referred to as maximum peak. Peak. The peak time is this time that it takes to reach the maximum peak. I've mentioned delay time, rise time. Delay time is to reach 50%, rise time is to reach 100%, between 0 and 100, or for systems which you don't have 100%, you can reach 5 to 95. We have maximum peak overshoot. This peak overshoot, it usually expresses a percentage of this overshoot. Peak overshoot. It indicates the normalized difference between maximum peak of the response curve and the steady state, given as peak minus steady state over steady state. And finally, we have settling time. Settling time is equivalent to the time which the system has stabilized, and it stabilizes when it reaches 98%. And not only 98%, to reach and stay. Reach and stay. Stay within 2% of final value. So you see, the 2% is 98%. That is the final 2%. That's the so at this point it reaches and it overshoots and it even comes down below 2%. But beyond this point, it has reached, and as the oscillations die out, it stays within this 2% band. You can use 2% criteria or 5% criteria. So it is known as settling time. And finally, steady state error is the error as time tends to infinity between the actual input signal and the output signal. So you find that as time tends to infinity, the error is positive here, negative, positive, negative, positive. But as time tends to infinity, error tends to zero. So finally, some comments. You have seen that in systems, we don't have all this specification does not apply, because in systems which are critically damped, you don't have the peak overshoot because it's critically damped or overdamped. You don't have the peak overshoot, and therefore you cannot define peak time. You cannot define peak time. Cannot be defined. And at the same time, rise time is defined separately. For this, it is defined as 0 to 100% for this undamped, and for this is 5 to 95%, or 10 to 90. Okay. Number 2 is just in practical systems, damping lies between 0.4 and 0.8. This is just a general comment. What happens beyond third order, higher order systems? We saw that we can factorize what do you call s power n, what is it called? Characteristic equation. This is a polynomial. We can get first order factors, and second order. Factors. The reason why we have second order factors is because they can be complex roots. Complex roots. So we combine two conjugates, two complex conjugate roots to get a second order factor. And first order. So first order with real roots and real coefficient, and second order. So any other higher order systems, we factorize into first and second order systems. And by studying response of each individual factors, study each factor individually, we can say that the overall system response is the sum of each individual system responses. So, and for that reason, we will not go beyond second order systems. We will not go beyond second order systems. So it is important that you remember this, because sometimes you can be told to sketch. Oh, this is an old one. Sketch. No, this was an exam for electrical students. You can be told to sketch the response of a second order system. Just trying to see. This does not concern you so much, but this is a very old see this. I'm just trying to see that you need to yeah, you see, like a question like this, for example, you sketch the response of a second order system to a step and define rise time, setting time, delay time. Yeah. You may need to, sometimes you may be asked, or you need to know all those definitions. But these were electrical students considered both amplifier, motor, gears, etc. So that's an example of some old work which I used to do in the 2016 there. Now, we have seen the response for first order. D of t to first order. It's just a summary. U of t to first order system, and U of t to second order. So depending, for a second order system, the response takes standard. If you put it in standard form and find delta of t, then not delta of t, standard form. I meant standard form. Then the response will take different forms. Or I've deleted the Fourier Laplace transform tables. Sorry. Yeah. You see, depending on the value of your damping, this takes standard forms. So we are only concentrated. We are only what do you call? Our factors was based on 0 to 1. The damping between 0 and 1. And this curve takes some standard form. For further reading, I will refer you to the textbook if you want to see responses of different scenarios. You can refer to the textbook by Ogata. Now, that's time domain. Now we want to check what happens in time domain. We have seen that we do partial fraction expansion, expansion for each first order root or a factor, and second order factor. Now, our polynomial transfer function is a polynomial in S. In S. Meaning, you can Q of S can be written as, not Q of S, G of S, as AS power M, A0 plus A1 S power M minus 1 plus all the way AS AM minus 1 plus a constant AM over B0 S power N plus B1 S power N minus 1 plus all the way plus BM minus 1S plus BM. Now, I need to factorize this to get the roots. Factorize to get roots. Such that it becomes S plus Z1, S plus Z2, all the way S plus Z M. Should I have started with 0? Should it be 0? Okay, whatever the case. S plus P1, S plus P2, all the way S plus Pn. So this is factorized to get the roots. If S is equal to negative Z1, then G of S is equal to 0. It makes, and Zi is referred to as zeros of transfer function. Roots. Roots of numerator are referred to as zeros. Roots. If S is equal to negative P1, then G of S is equal to P of S over 0. So G of S tends to infinity, and Pi are referred to as poles. So poles are roots of denominator. Zeros, I think not zeros, not this one. Zeros are roots of numerator. That is G of S transfer function is equal to P of S over Q of S. We don't have an issue with what makes our system goes to 0, because it basically means if you have an input, if you give it an input, and the zeros take the output to 0, meaning the output will be 0. We don't have a problem with the output being 0. But supposing you have an input, you give it an input, and the frequency, because S is the frequency, S is equal to frequency, complex frequency, so that the system operates at the pole, so that you give it an input and your system operates around the pole so that the output goes to infinity. Infinity. Supposing this output was vibrations, and you have a mechanical system. Supposing the output was vibration and it was a mechanical system, and the vibrations increase, it means your system becomes unstable and it will break down. Your system becomes unstable, it breaks down. Because the output, you are operating your system at around the poles, and therefore the outputs, the poles make your transfer function go to infinity. Poles make your transfer, the roots of the poles, which is the poles are the roots of the denominator, make transfer function go to infinity. Meaning, if you apply an input and you're operating around the poles, then the output becomes so high that your system now becomes unstable. So, in short, we are only interested in the characteristic equation, which is the denominator polynomial. We want to see the denominator polynomial. Which is Q of S. Now, we now know what is desirable. What is desirable is that the input should not increase without bound. The input should not go very high, because assuming the output was a voltage, if it goes very high, it burns your insulation, it burns your conductor. If your output was a force or a vibration or distance, if it is very high, it means your system breaks and it becomes unstable. Now that is the topic of stability analysis. Now, I was introducing stability, and we say that a system is stable if, when excited by a bounded input, the output is bounded. A system is stable only if you apply some bounded input, the output should be bounded. So G of S must guarantee that the output is bounded. G of S, the poles of G of S must guarantee that if you apply a bounded input basically means it has a maximum value, then the output should also be bounded. It should not go to infinity. Number two, another definition of stability is that when you have a system and you have removed the excitation, you have a system, you have removed the force, the output will tend to 0 in the absence of that input. That is, if you have a mechanical system and you push some force so that like a pendulum, it swings. If you continue pushing as sway, it's what you call a pendulum kind of seesaw. Seesaw. There'll be some swinging of some sort. But in the event that you remove that push, then the vibration should come to a stop. It will swing, 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 swing. A pendulum is an example of that seesaw. If you leave it, if you push it, the vibrations will die out with time. With time, the swinging will die out with time. That kind of thing. So this is known as asymptotic stability. If you have an input which is bounded, the output should be bounded. But if you withdraw the input, then the output should approach zero. The output should approach zero. Irrespective of the initial conditions. The output should, as time tends to infinity, the oscillations or the output will tend to zero. That's the second definition of stability. So a system is unstable when it is excited by a bounded input, the output is unbounded. Critically or stable system, when you apply a bounded input, the output is marginally stable, it does not increase or decrease. For example, if you apply, if you have some oscillations which does not die out, they are not increasing. They are not increasing, neither are they decreasing. This behavior is important in designing some systems. Like we want to generation of oscillations. In oscillators. To provide clock or frequencies in electrical systems. Of course, there are applications also in mechanical systems. So this is called critically or marginally stable system. The output does not decrease, neither does it increase. So it oscillates continuously. Conditionally stable systems. These are systems which are stable under some certain conditions or parameters. And if the parameters change, the system may become unstable. Now, we have said that we have a polynomial in S. Now, we do the roots, partial fraction expansion of the denominator, such that we have, let me go back. I expand this in this form I've shown, in this form. Now I can do partial fraction expansion of the denominator, of the entire transfer function, which can be written as A over S plus P1 plus B over S plus B P2 plus sometimes CS plus D over S squared plus 2 delta omega n S plus omega n squared. These poles, these roots, P1 all the way to Pn, if we have complex roots, then they are conjugates. Then you combine any two conjugates, conjugates, to get a second. So when you are to get a second order factor. So when you factorize any polynomial, a higher order polynomial, you'll always get a first order factors and second order factors. This has got a root at s is equal to minus pi. This has got root at s is equals to minus sigma plus or minus j omega I. Because these roots are complex, complex conjugates. One with minus sigma or plus or minus, plus or minus, plus or minus. The roots, because if it is s over, no, it's a over s plus 1. And we have a over s minus 1. The root of this occurs at s is equal to 1. And the root of this occurs at s is equal to minus 1. So the roots of this can occur at s is equal to plus or minus pi. Pi is a real number. The roots of this can occur at s is equal to plus or minus sigma plus or minus j omega. Sigma and omega are real numbers. Now, let's look at the effect of having a pole on the complex S-plane. S-plane. Now, I can now plot my S-plane, which is sigma plus j omega. It's S-plane. I can locate, if I locate my pole here, this is the transfer function 1 over s plus a. Pole, okay, the other thing, pole on the S-plane, poles indicated by zero, indicated by. So if the transfer function is s plus 3 over s plus 7, so s is equal to minus 3, I put a 0. S is equal to minus 7, I put a pole. This is a pole zero diagram. And from now on, we'll be dealing with pole zero diagrams. But for stability, we only want to investigate the denominator. That is the characteristic equation. Roots of characteristic equation. So if you have s plus a, your time domain equivalent is e negative at. We saw this from Fourier from Laplace transform tables. S plus a is e negative at. And if a is negative, say that it becomes 1 over s minus a. So this, for this case, S is equal to A. And S is equal to A, so A is basically A plus J0. So it is on the real axis. S is real plus J0. Yeah. And the output is that. We can say that this system is stable. But this system is unstable because this is only the system. So once you apply the input, any input, and as time goes to infinity, the output becomes increasing without bound. That is real roots. Let's look at when you have complex conjugate roots on the left. The first thing, once you have complex conjugates, once you have complex roots, not complex roots. Complex roots tells you that it is oscillatory. Complex roots indicate that there is some oscillation. But because they are on the left-hand side, just like when you had the real root on the left-hand side, it is decaying exponentially. When you have complex roots on the right-hand side, where is complex roots on the right-hand side, the response is oscillatory, but it is increasing. When you have complex roots, when you have complex conjugate roots on the axis, the response increases, or does not increase, or does not die. When you have one single simple root, like a step function, it was 1 over s, the output is constant. What does it tell us? Number one, when the roots are on left hand side, the response dies out. When on j omega axis, this is a j omega, the response is constant. When right hand side, the response is increasing. This is dying out. This is constant. Whether it is oscillatory, if the roots are, these are simple roots, If they are complex conjugate, complex, depending on where they are, then it means if they're on the left-hand side, then it is dying out, oscillating. When it is on the j omega axis, then it is, when it's on the right-hand side, so you can say that when the roots are on the left-hand side, the system is stable. Because it dies out. You see, it's dying out. When they are on the j omega axis, whether simple or complex, the system is marginally. And when they are on the right-hand side, the system is unstable. If we have also two roots, 1 over s squared, you recall 1 over s squared, 1 over s squared is like that, t. These are two roots, indicated as two roots. T should be a straight line, like that. 1 over s cubed, we have 3 of them. 3, it becomes an acceleration, like that. It accelerates with time. We also have, if we had, we have mentioned, this is simple roots. No, these are 2 roots on the j omega. This is 2 roots, double. When it is double, it also increases. So on the j omega axis, we only need to have 1 root. 1 root. 1 root for marginal stability. Now, this introduces us another definition for stability. We have said a system is stable if exerted by a bounded input, the output is bounded. A system is stable if once you remove the input signal, the output should die out. And number 3, now we know that a system is stable if the poles lie on left-hand side. Sometimes you call this, for a pole to lie on left-hand side, S is equal to negative sigma. Sometimes plus or minus j omega. So that becomes S plus sigma plus or minus j omega. If I combine these two, if it is complex, I'll combine these two. S plus sigma plus j omega and S plus sigma minus j omega. I'll combine these two. I get second order S squared plus 2 delta omega n S plus omega n squared. But if it's just a simple roots, so we'll say the poles lie on the left-hand side. Alternatively, we say it must have a negative real part. Negative real part. It doesn't matter the complex part. The complex part can lie on either up or down. But the negative real part is what the root must have negative real part, negative sigma. S is equal to negative sigma. This meaning S must lie on some negative sigma, whether it is real, simple or complex part. So, for a system to be stable, we have, in summary, we supply a bounded input, the output should be bounded. Or if there is no input, the output should die out asymptotically. Asymptotic stability. Number 3, poles on the left hand side, or I can say it should have negative real parts. How do I do it? I factorize my system. Factorize denominator. Into first and second order. The problem arises that we don't have any formula of factorizing beyond a quadratic equation. Of order 2. Though a professor of mathematics told me that there is an equation for order 3. For order 4, 5, 6, we have been using what we call remainder theorem, and those are only for real roots, are whole numbers. So we cannot factorize. If you have an order 6, if you have an order 6 equation, are we going to, how do you factorize order 6? It's difficult. Because we are supposed to factorize and then see the location of the roots. Are they on the left hand side or are they on the right hand side of the S plane? Of the S plane. And it's at order 6. We cannot factorize. Now, there comes now a criteria which was developed by somebody called Ruth. and Howitz. There is one which was developed by Howitz separately, and I think Ruth improved on Howitz. So sometimes this is called Ruth Howitz. We have Howitz criteria which we are not going to discuss. We have Howitz criteria we are not going to discuss, but we'll discuss Ruth Howitz criteria, or generally called roots. So when I mention roots Howitz or only roots, it's the same criteria. So we beyond a system of higher than order 2, we don't need to get the roots because it is difficult to get to factorize a polynomial of order higher than 2. So Ruth and Howitz criteria provide a simple way of judging whether the pole lie on the right-hand side or the left-hand side. Once we find out that there is a single pole lying on the right-hand side, we know that that system transfer function is not stable. Now, first, we are interested only the Q of S, characteristic question, the norm polynomial. We are interested in the nominal polynomial. We have to subject it into some array or table known as roots array or roots table. We have to subject so that you can determine whether there's a pole on the left-hand side or right-hand side. But first, before we subject it, there are some two prerequisites. Conditions. That it must fulfill before you subject it. Because if they fail these two, then it means it is unstable. The first is that the coefficient of S must be real and have the same sign. So A0 S power n, A1 S power n minus 1 all the way to AN minus 1S and AN. The coefficient A0 all the way to AN must be real and same sign. Number 2, none of the coefficients should be 0. You cannot have A0, A1, A3, A4. No. A2, none must be 0. We need to have all the coefficients from A0 to AN. After that, now we can say, let's subject it to Roth's table. Now, let's wind up. We wind up by just looking some few. We are not going to discuss the Roth's table today. We are just going to see some 2-3 characteristic questions, whether they meet these two conditions. If one of the coefficients is 0, it implies that there is one or more roots have positive real parts, or there is a root at the origin, or there is a presence of the root at j omega axis. Look at s squared plus a squared. S is equal to plus or minus a, ja. Because this is, ja. Meaning we have a pair of a. Because this s squared, there is coefficient of s is missing, 0s plus a squared. So it means the presence, if one coefficient is missing, then there is a presence of the root on the j omega axis. There is a root at the origin. If you have like s squared, s4 plus s cubed plus s squared, plus s, we are missing a coefficient of s power 0. This you can factor out as s power 3 plus s power 2 plus s power 1 plus s power 0. 1, 2, 3, 4, 1, 2, 3, 4. This root is at the origin. This root is at the origin because the term, the coefficient of s power 0 is missing. The other condition is that we have roots on right hand side. So if one of the coefficients is 0, it means that it may be unstable or marginally stable. But if the sign, if one of them, if the sign is different, then it basically means it is unstable. So this condition means if it's not fulfilled, it is unstable. If this one is not fulfilled, it either means it is marginally stable or unstable. Now, quickly we look at some examples. S power 5, s power 4, positive, 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 negative, positive, positive. So we have s power 5, 4, 3, 2, 1, and 0. All coefficients of s are present, but now there's a change in sign. Change in sign and stable. We don't need to subject it to roots table or roots array because we already know it's unstable. Number 2, s power 5, s power 4, s power 3, s power 2, s power 1. There is no s power 0. Now that we don't have s power 0, it means it either be unstable or root at the origin. So there is a root at the origin, but we don't know whether it is unstable. So we need also subject, if you factor out s power 4, you'll get s power 4. If you factor out s plus 5 s power 3 plus 3 s power 2 plus 2s plus 1. Now, this fulfills the condition. Now you also subject this to roots table or roots array. Example 3, s power 5, s power 4, s power 3, s power 2. We are missing s power 1. So it's unstable. Or, okay, it is unstable by the author of this example, but for us and me and you, it may be unstable, or we may be having roots on j omega axis. J omega axis is the complex axis, complex axis. Finally, in your notes, one of these, either this or this, is written wrongly. In your notes, it is written as wrongly, but I will send updated notes. So in your notes, I think it's either this or this which is written. I think it is this which is written wrongly. Let's look at this. S power 5, S power 4, S power 3, S power 2, S power 1, S power 0. And negative, 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 negative. So same sign, sign, all coefficients present. So this has fulfilled necessary conditions. Therefore, we subject it now to the roots array. We will subject to the roots array. This is what we will discuss next time. The roots array. Table or array. We basically use to determine whether roots of Q of S is on right hand side. For it to know that the system is stable or not. We are going to end there for today. And now I'm here for any comments, any text. Let me see, there's no text. Any comment, any question? Do you have any comment?